Hi, welcome to this session. In this session, what we'll do the analysis of the circuit that was given to you as an assignment. Here we have created the circuit in the multisim. Okay. Here, what we have in the circuit, we have 100-volt source connected into 10 ohm resistor, 10 ohm resistor, 5 ohm resistor, and there is a 10 farad capacitor. Now, these XM1 and XM2 are multimeters in this multisim, and we'll use them to measure the currents through R3 and this capacitor. Now, before we turn on this simulation and connected the source, what we'll do, if we do the theoretical analysis of this circuit, we know the time constant of this circuit theoretically comes out to be 100 seconds. Okay, so tau for this circuit is 100 seconds. So approximately how much time it should take this capacitor to fully charge? Now we know from the theory it will take 5 time constants, that is 500 seconds, because tau is 100 seconds, so it will approximately take 500 seconds to fully charge this capacitor. Now after the 500 seconds, capacitor will be fully charged and will act as an open circuit. So capacitor current at 500 seconds will approximately drop to zero, and all the current will be flowing now through R3. So that's what we are going to do. So at t equal to zero, we assume that this capacitor is not charged, so there will be no voltage stored, so it will act as a short circuit. We already know this from the assumption that was given in the circuit. So at t equal to zero, capacitor voltage is zero. That means it will act as a short circuit. So what we have at t equals 0, capacitor current, initial capacitor current will be 5 amperes. And the initial current going through this R through resistor will be 2.5 amperes. Similarly, at t equal to infinity or at t equal to 500 seconds, the capacitor current will drop to zero and all the current will be flowing through this R3. So what will be the current at t equal to infinity or at t equal to 500 seconds will be 100 divided by 10 plus 10, that is 100 divided by 20, that is 5 amperes. So let's prove these points. Okay, so let's start this simulation. As you can see, I haven't connected anything, so there is 0 amperes flowing through this R3 because the switch is not connected, and there is the capacitor current is also 0. Now, as I close this switch at t equal to 0, the resistor R3 current should be equal to approximately 2.5 amperes, and capacitor current should be equal to approximately 5 amperes. And after closing the switch and after 500 seconds, the capacitor current should drop to 0 and resistor current should be equal to 5 amperes. Let's observe this one. As I close this switch, look at the this resistor current. As you can see, resistor current is initially 2.5 amperes and capacitor current is decreasing from 5 amperes towards 0 as time progresses. Because the time constant of the circuit is very huge, that is 100 seconds, so we have to wait for 500 seconds to see let this capacitor fully charge and act as an open circuit. As you can see, the capacitor current is dropping as time progresses. So if we wait for 500 seconds, we'll see capacitor current will drop fully to 0, and this R3 current will rise to 5. As you can see, resistor current is increasing, capacitor current is decreasing from this. Okay. Now, because 500 seconds is very huge, what I will do, I will stop this. Instead of this, I will stop the simulation. This will fully charge the capacitor. So after fully charging the capacitor current should drop to 0, and resistor R3 current should be equal to about 5 amperes. Let's observe these ones. As you can see, resistor current is 5 amperes and capacitor current is 0. Okay. So now what we'll do, we'll study the discharging of this capacitor in this, as this part is not asked in the problem, but let's discuss this. Okay. So now if I open this switch, what will happen? This capacitor has voltage stored in, so it will act as a source. So what will be the direction of flow of the current? it will be reverse. As we know, at the time of switching, capacitor current reverses its direction. Let's observe these points. And also, you can see now current, as I open the switch, no current can flow through this. There, so the capacitor current will go like this. So it will flow through this 10 ohm, 10 farad capacitor current will flow through this 5 ohm resistor and this 10 farad 10 ohm resistor. So in other words, capacitor current and this R3 current are negative of each other. That resistor current is going like this, capacitor current is going like this. So because I have connected the pole plus terminal on this side, so capacitor current should reverse its direction or polarity. As you can, it will be negative. I open this, you can see as capacitor current is minus, and you can see the two currents are equal in magnitude. Only the capacitor current has reversed and it is direction. And after how many seconds? What is the time constant of this circuit? Time constant for this circuit will be resistance. Total resistance is 5 plus 10, that is 15, and then that means 150 seconds. So time constant for this circuit is now 150 seconds. That means after 5 into 150, that will be 750. So after 750 seconds, capacitor current will fully drop to zero, right? So it will take now capacitor, how much time? 750 seconds to fully drop to zero. All right. Now, let me change the resistance's value. Okay. Let me change the resistance value to observe these switching actions fast as the dropping of this capacitor current to zero quicker than this. So let me modify the circuit. Instead of having 10 ohm resistor here, let me write 2 ohm resistor here. Let me replace it by a 2 ohm resistor and this by a 1 ohm resistor and this capacitor by a 1 farad. This 1 farad value. Okay. So let me stop the simulation. Now you can see the capacitor current will be fully dropped to zero and so resistor current will also be equal to zero. Okay, let me modify the values. Let me write this equal to 2. Change this also to 2. This to 1 farad, 1 ohm, and capacitor to and capacitance to 1 farad. Oh, and you can see the new time constant for this circuit is now, it will be 2 seconds. As you can see, 2 ohm, 2 ohm, there is one. So if you do the theoretical analysis of this, so that new time constant for this, this will be now 2 seconds. So approximately how much time it should take this capacitor to fully charge? 10 seconds. Means 5 time constant, right? Time constant is 1. So time constant is 2. So 5 into 2 is 10 seconds. So after 10 seconds, capacitor should be fully charged. Okay. Let's observe this. Also, what will be the initial currents in the capacitor and this R3 resistor now? Okay. Now, what we'll do at t equal to 0, if you do the this analysis of this, the current comes out to be, the capacitor current comes out to be 25 amperes. Okay. And this resistor current comes out to be 12.5 amperes. So as time progresses and as time increases towards 10 seconds, so this capacitor current should drop to zero at 10 seconds, and this current should be, what should be this current? 100, 2 plus 2, that is 4. So 100 divided by 4, that is 25 amperes. So this current, resistor current, R3 current should increase to 25 amperes, and this current should drop to zero after 10 seconds. Let's observe these points. Okay, let me turn on the simulation. As you can see, there is no current because the switch is not connected yet. Okay, let me close this switch here. You can see the initial value of the R3 current will be 12.5 amperes, and initial current of this capacitor will be 25 amperes. Okay. And now there is a lag in the recording, so you may not see approximately here 12.5 and 0.5. But one thing you will observe that capacitor current drops to zero after 10 seconds, and this current will reach to 25 amperes. Okay, because there is a lag in the recording in these multimeters here that are given to us in the multisim. So after 10 seconds, we should observe that this R3 current should be 25 amperes and this capacitor current will be equal to zero. Let me turn on the switch. You can see, or as you can see, it starts recording the value. This, as the time goes towards 10 seconds, the capacitor current almost drops to zero. You can check it from here. Now it's in milliamperes. Okay, and resistor current has risen to almost to 25 amperes. Okay. So this is what happened after this. As time progresses, capacitor current almost goes to zero. It's now 3.5 amperes, 1 milliamperes. Now it has, okay, you can see it is now in microamperes, and resistor current is almost equal to 25 amperes. Okay. So capacitor is now fully charged and will act as an open circuit. So no current can flow through this. All right, all the current will be flowing through this R3, and that's equal to 1.5. Now what we'll do, we'll open circuit the switch and observe what will be the discharging behavior. So how much time it will take now to discharge this capacitor. Now in discharging path, there is this R2 and there's R3. Now, because no current can flow through R1 if I open this switch here. So what is the time constant, new time constant for this discharging part? 1 plus 1 is 1 plus 2 is 3, so 3 seconds. So after 15 seconds, this capacitor should be fully discharged. Now let me open circuit this. Okay, you can see. Okay, you can see the capacitor current is decreasing as time progresses. And why is the capacitor current reverse here? Because as we do switching, capacitor voltage cannot change instantaneously. That's why capacitor current has to reverse its direction. Okay, as you can see. And also the two currents in the R3 current and the capacitor current are same. Why? Because these are connected in series. Okay. These are the observations, some of the observations that we can see from this charging and discharging of this circuit. Okay, let me end this session here. I hope you understood.